Okay, this is the lecture video for MAC 1105 College Algebra. We're in section 5.3 where we're going to take a look at the properties of logarithms. In this section specifically, we're going to be looking at properties that will take you from a single log into its expanded form. And you see the various properties here. On the left side, you see the single log representation where you only see the word log one time. That's called a single log. And then you see the expanded version on the other side, specifically for the product, quotient, and power rules. These properties that you're seeing here, again, will be used very much in the next section where you try to master how to solve a logarithmic equation. A very big concentration of this chapter, so everything's kind of leading up to you being able to solve that type of equation, and these properties will come in very handy. So the first one is the property regarding, it's called the zero exponent rule, regarding the log of 1, any base, and that value is equal to 0. You can even put that in your calculator. When you put the log of 1 in your calculator, it will be 0. This one, you can relate this to what's called the inverse property, and I can extend this property for you. What this one reads is that log of a, where the argument is a, if the base matches it, then the value of this entire log expression will be equal to the number in the power position, or in other words, the exponential position. So if that argument, if it matches the base, whatever the power is, that is what this is equal to. So you can say this in a more extended form, in a more general form, that the log of anything, and I think I'll just use this, as long as the argument matches the base, then whatever is up here, even if it's not a 1, whatever the exponent is, it will be equal to that value, this entire logarithmic value. So you're just looking to get the argument equal to the base, and then those bases cancel, taking the log with it, and the exponent is the value that it is equal to. So that's called the inverse property. And we're going to be using that one a lot in order to simplify the expressions that you see in this section. And also we'll be using it a lot in the next section where we solve equations. This one's called the product rule, and this says that in its single log form, if you see a product, then the factors that make up that product, x and y, are both called factors that form the product xy. So you can expand a single log if you have a product using a plus sign. You will separate this into single logs. One factor will belong to the first log and the second factor will belong to the second log, both bearing the same base. So a product is split up using a plus sign. Okay, product becomes a sum. In the next property, you see the quotient rule. You're starting off with a single log represented as a quotient, and in order to expand that, it is log of the top, and in this order. Don't switch the order. It's log of the top, that'll be the first term in the expanded version, minus the log of the denominator. Okay, so a quotient becomes a difference. Split it up using a minus sign. Next one is called the power rule. And the power rule states, and notice that you will have 3 different levels here. A base all the way down at the bottom level, an argument right on the same level with the word log, and an exponent at the highest level. So that exponent, or power, you may use either word, that power is going to become a coefficient when you write it in its expanded form. Okay, this is called the power rule. Power becomes the coefficient. Notice that it's out front now, and now the power on the argument is just 1. So you're always going to apply that property when they say expand it. All of these properties can be used going forward to the expanded side or going from the expanded version back into the single log. That's mostly what you're going to be, the way you're going to be using these properties when you get into the next section. You will be presented with expanded versions, and you're going to bring it back to a single log in order to get yourself ready to solve the equation. Okay, we also have a formula that was introduced in a previous section called the change of base formula, and this allows you to go from whatever base they're starting you with, you see that the base is b here, into any base of your choosing. And you do so by knowing how to expand this. Okay, change of base formula says that you will create a fraction made out of 2 logs. The numerator will have log of the argument. That's the number right out in front of the word log. That'll play the role of the numerator. And then log of the base will play the denominator, log of the base. So whatever that hanging base value is, that will be your denominator, and then you get to choose what x is. You can choose the base that you desire. Okay, so that x value is your choice. The reason that this is good is because your calculator, when you press log, what's programmed into your calculator right here under log is base 10. That's why in its exponential form it says 10 to the x. When you press ln, the base is e. And because your calculator only does base 10 and base e, what happens if you get something like this, yet you're expected to find the value? Perhaps you would be asked to find the log of 7 base 2, but you have no keys on your calculator that can handle that. And so you have to know how to write this in an equivalent form that can be handled by your calculator. So if you were going to rewrite this, you'd be applying the change of base formula. Okay, and once again, what that says, I'll demonstrate it now with numbers, is log of the value right out in front of the word log will play the role of your numerator. And that's exactly what this says. Log of the value right out in front of the word, log is the numerator, and then the denominator will just be log of this base. And since you get to choose the base that you are now changing it to, it was base 2, which cannot be put into your calculator, you can designate that this is base 10, thus allowing you to find the value of log of 7 base 2, but in an alternative form where you have changed the base. The value of this is equivalent to this. So you may change to any base you want, and then you'd be able to get a decimal approximation for log of 7 base 10 divided by log of 2 base 10. You would just press it in just like that. You would press in the top value, log of 7. Now when you press in a log of anything, it understands that you are doing it in base 10. It only does base 10. So even though there's no little 10 hanging off of the word log as the base, it is said to be 10 when there is no number, when there's no base listed on the log. So it's log of 7 divided by log of 2. And there you have a decimal approximation. And you can round, they'll tell you what to round it to. I'm just going to round this to 3 decimal places. This is approximately, the approximation symbol, 2.807. Okay, and that's equivalent to log of 7 base 2. So change of base formula. Okay, now let's take practice applying each of these properties that I have just reviewed with you above. Each time I will point out which property I'm using. Okay, so in this one, this is the, and look at the directions. It says use the properties of logarithms to expand the logarithmic expression. So notice here that you see a product, and you are using the product rule. You expand a product by taking each factor in the product and creating its own individual logs separated by a plus sign. So these terms are the sum that represents this product, but in its expanded form. So this will be equal to log of 9 plus log of 7, and both of those logs will bear the original base. Okay, you can go further with this. One of these terms can be more simplified. You can simplify it further, and that would be this one. This one right here, you can apply the inverse property. If you can rewrite this argument such that the base of the argument matches this right here, then you can simplify it by the inverse property. Let's review that property. Here it is right here. When you have the log of a number and it matches the base, then the exponent is what this whole value is equal to. And I'm going to apply that here. I'm going to rewrite my 9 as 3 squared. The base is 3. When the argument matches the base, they cancel, take the word log with it, and the entire value that represents this log expression is whatever the exponent is. There's no way to rewrite this in terms of 3. So just bring it down. It is as simplified as it can be, and that is the final answer. Okay, moving on to the next one. This is also a product. It's 343 times x. Anything that is a product gets split up using a plus sign. Okay, so a product is split up as a sum. Same thing is going on here. This will be log of 343 plus log of x. You separate it into individual logs. Each of these individual logs gets a factor from the product, and then the bases will be the same as they were in the original problem. Then you have to ask yourself, can I simplify further? And very, very often that inverse property is what's allowing you to simplify further. So I want to ask myself here, is there a way to write 343 in terms of 7 to some power? So I'll just try it out. Try it out in my calculator. So I'll go 7. I'm going to try raised to the 3rd. There we go, right there. I knew 7 squared was 49. Most of you are familiar with that, so I just went a little bit higher, and I already hit it. So this log of 343, I'll write it over here, so I'm not going into that problem. This log of 343 is the same thing as 7 to the 3rd. That's 343, and it already had a base of 7. So because this argument matches this base, they cancel. Take the word log with it, and this is equal to whatever is in the exponential position. That other term cannot be simplified any further, and therefore it is just brought down into the final answer. Log of x, base 7. And that's your final answer. Okay, then this next one, this one's a quotient rather than a product. Reviewing that property, log of a quotient is just log of the top, that's what you see here, minus log of the denominator. So quotients are broken apart using a minus sign. They become a difference. So what you're seeing here is going to become log of 64, that's the top or the numerator of that quotient, minus log of 4. Both of these have the same base as the original quotient. Okay, you can simplify these further because both 64 and 4 are you're going to be able to apply the inverse property. The 64 you're going to have to rewrite. That is the same thing as 4 to the 3rd. And this one you don't have to rewrite it because the argument already matches the base. Excuse me that I write my 4s differently in one moment than I do the next. I write them 2 different ways. But they're both 4s. So anyway, when the argument matches the base, they cancel. Take the word log with it, and whatever is in the exponential position is the value of that entire log expression, but in its most simplified form. Here again, the argument matches the base, takes the word log with it, and whatever's in the exponential position. And when something doesn't bear an exponent, it is said to be a 1. So this is equal to 1. Bring that minus sign down. So that is equal to 2 in the end. That's your final answer in its most simplified form. Okay, moving to the next page. Plenty of examples for you. Some of them have been taken right from the software where you're going to be doing your homework. Okay, and number 4. This is again a quotient, and quotients are taken apart using minus sign. Quotient becomes a difference. Okay, I will make a comment that when you don't see a base on ln, it is e. It is always the same base for natural logs. The base is e, and you might want to put it there just so you recognize when the inverse property applies, which it does in this very first term. Argument matches the base, takes the log with it. And whatever is in the exponential position is what the value of this term is in its simplified form. You cannot write a 13 using a base of e. And e is just a number if you're forgetting that. It's 2.7 and it just goes on and on and on. There's many numbers after the 7. It's like pi. It's an irrational number. So you cannot make a 13 out of an e. So just bring it down, ln of 13, base e, and it's optional whether or not you write that e. You can write it or not. When there is no base written on a natural log, we know that it's an e. And that's the final answer. We were able to simplify the first term, but not simplify the second term any further. Okay, next thing you see is the power property. And the power property, you'll see 3 levels: a base, an argument, and an exponent. That exponent or power comes out right in front of the log, whatever kind of log it is, and becomes the coefficient of the log expression. So now the argument will have a power of 1, same base as the original, and that's as far as you can go there. Moving to number 6. Here, some students don't see the power because they have forgotten how to rewrite a radical in power form, so let me review that. Underneath this radical, you have an x to the first degree. When you're going to write this in power form, it is written like this. Okay, no radical now. A radical becomes a fractional power. The fraction has a 1 on the top. That'll be the power attached to this radicand, as it is called, underneath the radical. And the 13 will be the denominator of this fractional power. And that's how you go from radical form to fractional form. But now you have a power. And because you have a power on a log, you can use the power property for logs, whereas before this didn't have a power. A power becomes a coefficient, just as demonstrated in example 5. So this will be 1 over 13, now acting as the coefficient in front of the log. And now instead of having, a fractional power, this just has power 1. That's what happens when you apply the power property. Your argument will then have a power of 1. Okay, moving to number 7. In number 7, we're going to be able to apply more than one property, but first we're going to take apart the product with a plus sign. A product is expanded using a plus sign. So here is one factor belonging to the product with that base of b, just as in the original, plus this is the other factor belonging to this product. Base of b. Okay, so now we have taken apart the product, but we can still apply the power property. You are not to leave any of the arguments with powers any higher than power 1. So bringing this down, it becomes a coefficient. So the most simplified version of this answer is 5 times log of y base b. And this, there's nothing, this term, this second term, there's nothing more you can do to it. So that is the most simplified version in its expanded form. Okay, moving to number 8. In problem number 8, again, we see the radical, but that radical, you want to be able to write it in power form. But first, the first thing you're going to do when you're expanding is take apart either the product, if there's a product, or the quotient. Here we take a quotient apart with a minus sign. So it is log of the top, same base that you started with, minus log of the bottom. And again, same base. Okay, now we want to try and see things that we can do to help ourselves simplify further using the properties introduced on the first page. We can use the inverse property here. 125 is 5 to the third. And then right here we can write this in power form if we recognize that radicals can be written in power form. You have the expression x plus 5 to a power of 1. The index, when you don't see 1, is said to be a 2 on a typical square root. So this can be written, as I did in a previous problem, radicand. Now it's going to have a power. This would be and the power is fractional. This will be the top of the power, and the 2 will be the bottom. So now you have a power on a log, also base 5. Anything that you're writing in your expanded version has the same base as the original. Okay, now we can go further. Now that we've rewritten things, demonstrating how you can continue to simplify using the properties, we have the inverse property here. Argument matches the base. They cancel. Take the word log with it. And whatever is in the exponential position is what this simplifies to. What can be done to simplify this further, because you are not to leave your exponents on the argument of your log with anything other than a 1. So therefore we're going to apply the power property. We will bring that exponent right there, right in front of the log. So it'll be minus the coefficient, which was the power, and then your log expression. Log of x plus 5. And put that base right back there. Okay, so I was able to simplify this all the way down to 3, and I was able to simplify this somewhat by bringing the power down as a coefficient. Okay, then moving to this one. When we go to this one, let me just separate this out. We have a quotient first, but we will be able to once again apply more than one property. So we have a quotient, which we will take apart using a minus sign. It is always to take it apart, log of the numerator, base b, that's the base in the original problem, minus log of the denominator, base b. Okay, we still have a product though. So we had a quotient, we took that apart first. Now we're going to take apart the product. I'm going to write it going this way so I don't keep going into these problems. Okay, so to take apart this product, it would be log of x squared, that's one factor of the product. We take products apart using plus signs, plus log of y. Both of these would have a base of b. And then it's minus log of z. And then you look through your terms and see if there's any other properties that you can apply. And there is. In the first term, you can still apply the power property. where you take this, swing it out as the coefficient that lands right in front of the log. So that you're reporting just log of x, base b, log of y, base b, and log of z, base b. And that's the most simplified version where you've applied as many properties as possible. Okay, there was three properties applied there. We did the quotient rule, splitting this quotient up using a minus sign. Then we used the power rule, where we broke up, not the power rule, excuse me, the product rule, where we broke up this product using a plus sign. So it's log of x squared plus log of y. Then we used the power rule at the end. Okay, and that power rule just says that the power becomes a coefficient. So 2 times log of x plus log of y plus log of z, all base b. Okay, here we have a quotient to deal with. So this is equal to log of the top minus log of the bottom. And there's 1, 2, 3, 4 zeros there. Okay, when there is no base written on log, it is said to be a 10, and you might want to put it there just to help you recognize whether or not the inverse property applies, because that is often one of the steps that is used to simplify. Okay, can't simplify this because this is not the same as this, so that inverse property doesn't work, but it does work here because you can rewrite 10,000 as 10 to the 4th. Means it has 4 zeros on it. Okay, and if you're not sure of that, then 10 raised to the 4th. See, that's 10,000. Anyway, by doing this, putting it in power form, you now are in a situation where the inverse property applies. This argument matches the base. They cancel, take the word log with it, and you get this as an answer. For that second term after the minus sign, the entire value that this is equal to is 4. The term before the minus sign, you cannot simplify that any further, so it's just log of z base b. Okay, moving to number 11. In number 11, this is a natural log. Natural log has a base of e and only e. First, I'm going to apply the quotient rule. It's log, natural log of the top, minus, okay, we take apart any kind of a quotient using a minus sign. So a quotient becomes a difference. So it's log of the top minus log of the bottom, both with base e. Whereas it might not be so important to write it here, maybe you want to write it here so you can see that this argument matches this base, thus they cancel and they take the log with it. And what's in the exponential position is what this entire term simplifies into. And then when you write ln of y, it is your choice as to whether or not you want to write that. When there is no base written on natural log, it is said to be an e. It's the only base that natural log can have. Log can have different kinds of bases, but if you don't write one, then it is taken to be a 10 on log. Okay, so moving on to number 12. Got a radical there again. We're going to want to put it in power form since we're doing log problems, and there's a power rule. So you want to express any kind of a radical as a power. But first, let's deal with the quotient. Let's deconstruct that quotient into a difference. So it is log of the top, base 12, minus log of the denominator, which is cube root of y. Okay, let's review this right here, log of 1. Okay, here's that very first property, log of 1, any base is 0. And you can even, put that in your calculator if you forget it. That one you don't have to memorize because you can put it in your calculator. So, see, log of 1, any base, 0. So on the problem that we are presently doing, we have that situation here, log of 1, base just happens to be 12, but it can be any base. Doing log of 1, it is equal to 0. Then right here, you're going to want to rewrite that in power form. The power on the radicand is a 1, and in full exponential form or power form, whichever you want to call it, it is 1/3. A radical just becomes a fractional exponent. So we have nothing minus, you're not going to want to leave this power here, but instead you're going to be expected to apply the power property to any log expression. That power property says that the power becomes the coefficient. So yes, it still will be negative, but that power will now be in the coefficient position, out in front of the word log. Okay, and the bases that were on these things were 12s. Make sure to put that back when you are feeding in your final answer. Okay, that takes me all the way to 12. Going to the next page. We have one more expansion problem, numbers 1 through 13, all under the same instructions. And so you have this one, a little bit more complicated, but we'll deal with it. Okay, so this is a quotient. First thing we're going to do is take that quotient apart. We're going to deconstruct that quotient as log of the top minus log of the bottom. And the bottom is 7th root of x plus 16. Okay, if you want to continue working on the first term, this is a product. So you're going to go deconstructing the product using a plus sign. So it'll be ln of the first factor making up this product plus ln of the second factor making up that product. Okay, I'm going to leave that alone for a bit. And I'm going to come to this third term and I'm going to write it in power form. This expression occurs one time. These two are bound together. So you have to leave them intact. That's why you should put a parenthesis around them. If you're going to remove the radical, that means you're going to write it in power form. So it's ln of x plus 16 to the 1/7. Okay, next, see if there's anything else you can do. As you look at these three terms, every single one of them has a power other than 1, and you're expected to leave a power of 1 on all your arguments. So, in other words, you are applying the power property. Bring that 14 out in front of that natural log, and you've gotten that power to be a 1. Same thing here. And same thing here. And that's as far as you can go. You've applied a quotient property here, a product property to break that up, a power property to rewrite this, and then the power property was applied in all three. Well, we rewrote the radical in power form, and then we applied the power property to the first term, the second term, and the third term. So that's your final answer. Okay, when we get to 14 through 22, I believe it is, we are doing the reverse order of things. This time, You're given an expression in its expanded form and you're going all the way back to condensed form. Just what it says here. You're going to condense it. Condensing it means that you're going to take what you're given and you're going to write it as a single log. So that is what's happening in each of these problems. Okay, to condense the logarithm means you're writing it as a single logarithm. So you should only see the word log, L-O-G or L-N, one time. And you're going to apply the property. If this was given as separate terms where there was a plus sign between them, that means it used to be a product when it was a single log. So you're going to write this as a single log and make a product out of these individual arguments. So you can write x times 15 or 15 times x, but of course this is the way we write things. Number first, then variable. Okay, likewise here. You have a log of 2 plus a log of 50. So if there's a plus sign separating these individual logs, that means when it was a single log, it used to be a product because of this plus sign. Just like I was looking at the plus sign here. So I'm going to put these back together as the factors that made these individual logs. 2 times 50, base is 10. I'm going to go further because I want to apply the inverse property whenever possible. 2 times 50 is 100. Still with a base of 10. Log of 100 is the same thing. I want to rewrite this so I can apply the inverse property. So if this base is 10, I want to rewrite this 100 using a base of 10. So I've got a base of 10 on this log, and I'm rewriting my 100 as 10 squared. In that way, the argument matches the base. They cancel, take the word log with it, and this is equivalent to whatever is in the exponential position. Okay, moving to the next one. This time I see a minus sign separating the individual logs. Well, if something is in its expanded form with a minus sign separating the individual logs, that means it used to be a quotient before it was expanded using this minus sign. So list your log one time, base is 6. And make a quotient out of these. Whatever is mentioned first will be the top of the quotient, and whatever is mentioned in the second log will be the denominator. Keep going with this because you can oftentimes simplify these using the inverse property, so always try if possible. 48 divided by 8 is 6. But we also have a base of 6, so the inverse property applies here. If the argument matches the base, they cancel, take the word log with it, and whatever's in this power position is what this entire log expression simplifies to. Okay, moving to number 17. In number 17, again, there's a minus sign separating these individual logs. Therefore, this used to be a quotient. So applying that quotient rule, but going backwards to a individual log. What's mentioned in the first log is the top of the quotient. And what's mentioned in the second log is the bottom. And leave it there. If you don't put a base, it's said to be a 10. They didn't put a base here. You don't need to put one, but you can put the 10 if you want. Okay, so this whole thing is your argument in quotient form. Okay, moving to 18. In 18, you have a plus sign. That means these individual logs belong to a product. I also see a coefficient here. Anytime you see a coefficient, I would swing that right back up to where it used to be. So this is really log of y in a more simplistic form, going back to a single log and this would have been log of z to the 9th if you swing that 9 back up into the exponential position. Now putting this back together as a product. If as separate logs, it's a plus sign in between the individual terms. It used to be a product when it was a single log. So it'd be product means multiply each of those individual arguments. Okay, moving to 19. In 19, I see that these both have powers. I'm going to swing them both. They both have coefficients, so that means they both used to be powers. I'm going to swing the 2 back up here and the 9 back up here. Do not take the negative with it. You just swing the powers back up here. So this is what I'm looking at. ln of x plus 9 to a power of 2, that used to be a power, minus ln of x to the 9th. Now put them together as a quotient. Okay, so as a single log, this would play the role of the numerator. And this would play the role of the denominator. And that's it. You don't need to put a base there. When nothing's there, ln, we know the base is e. Okay, moving to number 20. Number 20 has more than a couple of terms for the first time. So I would like to state that if you do have a mixture of pluses and minuses, any terms that are positive in their coefficients that are out in front of them, those belong to the numerator. This belongs to the numerator. This belongs to the numerator. But anything that comes after a minus sign belongs to the denominator. Okay, you might want to swing those powers back up to where they belong before you continue with this problem. So look at it as ln of x to the 6th plus ln of y to the 3rd minus ln of z to the 4th. So all of those coefficients have swung right back up into the power position, and now I'm going to decide what to form a product out of and what to form a quotient out of. Okay, so again, anything that is positive, a positive term, those are things belonging to the numerator. Now we can only use the log one time. This is going to go in the numerator in the form of a product. Things that are positive, they will be multiplied together in the form of a product. Anything that comes after the minus sign will be part of the denominator. Okay, and that entire thing is your new argument in single logarithmic form. It's a natural log. You don't have to write the base. Okay, a few more of the expanded versions, 2 more, 21 and 22, because 23 is just change of base problem. Okay, so in 21, again, we have a mixture of plus and minuses. We have a positive term here, positive term here. The terms that are positive belong in the numerator. And anything that comes after the minus sign belongs in the denominator. So this is going to be ln of, okay, we're going to make a product out of the positive numbers. This belongs in the denominator because of that minus sign. Okay, let's continue. 46 times 27. That would be 1242. And then there's a 2 down here. Let's continue further. 1242 divided by 2 is 621. So this is ln of 621. You can put it closer if you want to, but it's base e. And that's your final answer there. Okay, 22. Again, we have coefficients out front. I would swing those up first, putting them right back where they were before this expansion happened. Okay, so you can look at it in a little cleaner form as log of x to the 16th power base 2 plus log of z to the 17th power base 2. Then you can go for putting this plus sign together. Things that are added together belong to a product. So in single log form, this would be log of x to the 16th multiplied by z to the 17th base 2. Okay, last problem. Last problem, we're doing a change of base formula, and as I stated on the previous page where I gave you an example of this, you can change from any base into base 10, especially if you want to put it in the calculator. And if someone's asking you for an approximation, you have to do it in base 10 because that's all your calculator will do. So you're going to comply with the directions in the front, ultimately put it in base 10 for the back if you're going to put it in into the calculator because they're all equivalent. So let's start with log of 2 base 9, and we're going to go from base 9 to base 10 for this first set of answers. Okay, so when you're switching over to a base, you just go, you look at this right here, and go log of 9. That'll be your numerator. Oh, sorry, messed up. That's log of 2. I drew the arrow there, but then picked up the other number. Okay, so it's log of the number out front. That's going to be your numerator. And then log of 9, that's that little tiny number you see there, the base. That it always plays the role of the denominator. They said to do it in base 10 because you're actually allowed to, let me give myself some more room here, you're allowed to choose any base you want, but of course you're trying to comply with the instructions here. Okay, so that's what you would feed in right here. I can't fit that whole thing there, so I'll just say log of 2 base 10 over log of 9 base 10 is what you would feed in right there. Okay, then if you want something that's equivalent to this, you feed it in using the base 10s. So just like you see right there, log of 2 base 10 divided by log of 9 base 10. Log of 2, when you don't see a base here, it's said to be a 10, divided by log of 9. And it's a decimal approximation and round to whatever they ask you to. So 0.3155 because they're asking you to round to 4 decimal places. So this is just an approximation, 3155. Okay, moving on to this next one. This next one says convert log of 14 base 6 from base 6 to base 5. Okay, so we can convert it to any base we want, but you're still going to start off the same. A log on top, log on bottom. It's log of the number right out in front of the word log, and then log of this little base. That plays the role of the bottom. They said to go from the base 6 it used to have to base 5, and you're allowed to go into any base you want. So this is what you would feed in right here. You would go log of 14 base 5, then divided by log of 6 base 5, complying with what they asked you to do. But if you're going to get an approximation, no matter how you write it, it's equivalent to what you started with. So just so you have the ability to do an approximation, you have to write it in base 10. That's how you have to enter it if you're going to put it in the calculator. So still log of 14 over log of 6. But to put it in your calculator, you have to do it base 10. And your calculator assumes you're doing nothing but that when you enter it when you try to enter it in the calculator. So it's just log of 14 divided by log of 6. And to 4 decimal places, that would be 1.4729. Okay, moving to the last one. Last one says do log of 8 base 19. Take it from base 19, which is what it is right now, to base e. And you can write it like this. Log of 8 over log of 19 base e. You can even write it like this. ln of 8 over ln of 19 base e. But when you're going to put it in the calculator, you're going to have base 10. So it'll be log of 8 still on the top and log of 19 on the bottom. And then you'll get that decimal approximation. So log of 8 on the top divided by log of 19. And that decimal approximation is to the 4th decimal place 0.7062. Okay, that completes section 5.3 for college algebra.